Alright, so today I want to go over a really elegant equation called the rocket equation, and sometimes it's called the ideal rocket equation, or it's named after its first inventor. It's named after Zolfsky, I think, but that's besides the point. It's basically just wanting to tell us the change in velocity after the mass is expelled. And in this case, the mass being expelled is the fuel. So let's get started. So I want to just first note that there's a before and after, which is before is when the mass is still in the rocket, and the after is when it's left the rocket. And this is just important to note because if you recall, momentum is conserved. So we should have P before equals P after. And you should know this, and this does just look like a simple explosion, right? So what is our P before, right? And notice how I've written out the system here in green. The system includes both the rocket and the gas inside of it, the fuel inside, and it doesn't change. The system doesn't change, and as far as we're concerned, we're not going to deal with gravity right now, so there's no outside forces. So that means in this case, momentum should be conserved, and this is our system. So anyway, to get started, the P before is equal to the mass of the rocket, which I've said is m, times the velocity of the rocket, which will be v. And it should be equal to P after, which is going to be equal the new mass, which is going to be m minus the differential of mg. So a slight increase in the mass of the gas, right? So like in this before, I'm not saying there's no gas left, but there's still some gas, right? But there's fuel in the rocket. And by the time it gets expelled, dmg is an addition to the gas. So it's important to state that dmg is mass of the gas. So continuing on, we're going to have this times a velocity, right? Our new velocity, which is going to be the original velocity plus a small increase in that velocity. And then we also need to consider the momentum of the gas, right? So we're going to plus this small mass called dmg times, well, the velocity, let's just say that it's expelled backwards at u meters per second, right? Well, since this rocket is traveling upwards at v, then the velocity to our reference frame here on Earth is going to be equal to v minus u. So that's what I'm going to put here, v minus u, just like that. So now, from here, we're going to need to expand. So if we just keep this side the same, mv is equal, and then we just start expanding. And let me just write down that this first half is the P of the rocket, so the momentum of the rocket, and this part is momentum of the gas. So let's work with this here. So if we have mv, I'll draw this m slightly better, mv, well, if we start multiplying, we have mv right here. Those will nicely cancel in a second. We have mdv, just plus mdv. And then we have minus v dmg. And then we have minus dmg dv. So that's our momentum of the rocket expanded. But we have to first also figure out the gas's momentum expanded out. So we're going to have v dmg minus u dmg. So from here, we can do all of our canceling business. Notice how these two will right off the bat cancel, and then these two will right off the bat cancel. And this gives us something that looks like this, which is going to be mdv minus dmg dv is equal to u dmg. And now it's here that I would like to tell you that, and like to mention, since this dmg mg and dv are both two differentials multiplied by each other, this number will be so infinitesimally small, we just don't even need to worry about it anymore. It's basically zero in this calculation. So actually, we can just move this on over and carry on with our day. And now the second thing I want to tell you is that dmg is also equal to the loss of the original mass. So notice how mg is mass of the gas, right? Well, m is going to be mass of the rocket. So I should put it's a differential of m. Because if we are adding this bit to the gas, we're subtracting a very small amount from the rocket. So these two values are really equivalent to each other because it's just a notational thing at this point. So we have mdv is equal to u dmg. And u is actually just the escape velocity of the gas. So u is equal to the velocity at which gas is expelled. So from here, it's just a matter of a really, really simple integration problem. So if we just do our separation of variables as you learn in almost all calculus classes, you're going to get something along the lines of u dmg over m, like this. And then we can integrate with respect to both sides, right? But it's important to note, what are we integrating this side to? Well, we're integrating from the original velocity, v0, to v final, right? So this ends up giving v final minus v initial, and this is just equal to delta v. So that's our delta v portion of that side. And now as for this one, what are we integrating? What is our limits of integration, right? Well, we're integrating from the original mass, so the original mass including the gas, and we're integrating across to the mass final, which is actually slightly less. So it's important to note that. And now if you apply just your simple basic integration rules, you're going to get u ln of what? Well, it's actually going to be u times ln of mass final minus natural log of mass initial. But the keen-eyed among you may realize we can use our natural logarithm properties, or just logarithm properties. So this ends up giving v, change in v, is equal to u times the natural log of m final over m initial. But there is a slight problem. M final is less than m initial by our definition of this very problem, the rocket equation, right? The mass of the rocket is decreasing. So that means this is going to be, the argument of this natural logarithm is going to be less than 1, which gives us a negative number, which is just a little bit ugly when it comes to doing these calculations. So in order to make it a little neater, we're going to raise this inside to the -1 and then put the outside to negative, and then bring a negative outside. So remember, if you flip these two on the inside, you have to throw a negative on the outside to keep things all equal. And I'll prove that in a second. But anyway, if I just write that down, that gives us this equation as our final rocket equation. And notice, if you remember your natural logarithm properties, you can take this and bring it over. And actually, no, bring it up. My apologies. Because technically, m final over m initial is equal to m initial over m final to the -1. So if you bring this negative onto the front, it becomes negative in front of the logarithm and in front of the constant u. And it's good to write that u is equal to v of the gas being expelled. So you can write that delta v is equal to our negative, like this, times the natural log of initial mass over final mass. And this is our completed rocket equation. And isn't that just beautiful how that all works? How this all of this complicated math, or actually not really quite complicated math, is some of the basis that launches rockets to the moon. And if you want to stick around till next time, I'll be discussing how this works in conjunction with gravity and other forces. Because although the formula is very similar, it is just slightly different to account for gravity. All right, thank you.